Dear students, in this video lecture, we'll discuss Unit 3, that is Order, Relation and Structures of your open elective paper, Discrete Mathematics and Applications. The code is MT454. Unit 1 is Number Theory and Cryptography, which is already discussed. And Unit 2 is Counting Principles. Now, the prerequisite for Unit 3 is Theory of Sets. I hope you are familiar with the theory of sets. But anyway, let us recall some of the basic requirements from set theory. So to begin with, what is the definition of a set? Set is a collection of well-defined objects. Well-defined objects is important there, because if I take in a class students who are intelligent, then this collection is not well defined. On the other hand, if I take in this class the students who scored A plus grade in the university examination, then this collection is well defined, because as far as grading system is concerned, A plus grade is well defined. It remains the same with respect to me or anybody else who considers the element under consideration. Now, once set is defined, you can talk about partition of a set. For example, in this figure, if you see a collection where it is partitioned into different parts, part A1, A2, A3 and so on up to there are 9 parts here. So what is a partition of a set? For example, here, suppose that S is the collection of numbers 1, 2, 3, 4, 5, 6. These are well defined. The collection of sets A1, which consists of only 1, 2, 3, A2 is 4 and 5, and A3 is a singleton set consisting of 6. This forms a partition of S because these sets are disjoint and their union is S. Now, what is a Cartesian product of two sets? If you take A and B as sets, then Cartesian product is A cross B. It is a set of all ordered pairs A comma B, where the first element A belongs to the set capital A and B belongs to the set capital B. Yes, now let us discuss what we call a relation. The most direct way to express a relationship between elements of two sets is to use ordered pairs made up of two related elements. For this reason, sets of ordered pairs are called binary relations. In this section, we introduce the basic terminology used to describe binary relations. So what is a relation from A to B, set A to set B? We can define a binary relation from A to B as a subset of the Cartesian product A cross B. In other words, a binary relation from A to B is a set R of ordered pairs where the first element of each ordered pair comes from A and the second element comes from B. We use the notation A related to B, ARB, to denote that ordered pair A comma B belongs to R, and A not related to B to denote that A ordered pair A comma B does not belong to R. Moreover, whenever A comma B belongs to R, A is said to be related to B by R. Now, we can define functions as a particular case of relations. So recall that a function f from a set A to a set B assigns exactly one element of B to each element of A. The graph of f is a set of ordered pairs A comma B such that B is f of A. Because the graph of f is a subset of A cross B, it is a relation, binary relation from A to B. Moreover, the graph of a function has a property that every element of A is the first element of exactly one ordered pair of the graph. Conversely, if R is a relation from A to B such that every element in A is the first element of exactly one ordered pair of R, then a function can be defined with R as its graph. This can be done by assigning to an element A of A the unique element B belonging to B such that the ordered pair A comma B belongs to R. Relations are a generalization of graphs of functions. They can be used to express a much wider class of relationships between sets. Recall that the graph of the function f from A to B is a set of ordered pairs A, f of A for A belonging to A. Now, once the relation is defined from a set A to B, we may ask, can we define a relation on a set A? Yes, it is possible, and these are of special interest. So a relation on a set A is a relation from A to A, or in other words, it is a subset of the Cartesian product A cross A. Now, how many such relations exist? We'll ask this question later. Let us take an example here. Let A be the set 1, 2, 3, 4, which ordered pairs are in the relation R. R is set of all ordered pairs A comma B such that A divides B. So both A and B are positive numbers, integers, and A should divide B. You know that 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4. So all these ordered pairs 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4 lies in R. What else? 2 divides 2 and 2 divides 4. So 2 comma 2, 2 comma 4 is there. Then 3 divides 3, so it is there. Then 4 divides 4, so 4 comma 4 is also there. And these are the only ordered pairs that belong to this set R. Now these relations can be represented by means of a table given in this form. Say 1 is related to 1, so make a cross mark there. Then similarly 1 is related to the corresponding row, corresponding column, you have a cross mark. If you see 3 and 4, the row corresponding to 3 and column corresponding to 4, there is no cross mark at all. That is 3 comma 4 does not belongs to R. Another way of representing this relations is using digraphs, directed graphs. So 1 is related to 1, so there is an directed line from 1 to 1. Similarly 1 is related to 2, direct a line from 1 to 2. Similarly 1 to 3, 1 to 4. And 4 is related to 4, so from 4 to 4 there is a directed line. So this gives a directed graph of the relation. Right. Okay. Now let us ask this question. How many relations are there on a set with n elements? If a set has n elements, how many relations you can have on this set? So we have to go for counting principles. A relation on a set A is a subset of A cross A. You know this. So to count the number of relations, you need to count number of subsets that can be constructed on A cross A. Now A cross A has n into n, that is n square elements when A has n elements. And you know a set with m elements has 2 to the power m subsets. Therefore, there are 2 to the power n square subsets of A cross A. So that is exactly the number of relations we can have on the set A. For example, there are 2 to the power 3 square, that is 512 relations on the set A, B, C. Okay, this set has 3 elements, so there are 2 to the power 3 square relations possible. Now let us discuss some of the properties of relations. There are several properties that are used to classify relations on a set. We'll introduce the most important of these here. One of them is reflexive, then symmetric, antisymmetric, and transitive properties. In some relations, an element is always related to itself. For instance, let R be the relation on the set of all people consisting of pairs x, y, where x and y have the same mother and the same father. Then definitely x is related to x for every person x. Such relations are known as reflexive relations. So what is a reflexive relation? A relation R on a set A is called reflexive if the ordered pair A, A belongs to R for every element A belonging to A. Using quantifiers, we see that the relation R on the set A is reflexive if for all A, the ordered pair A, A belongs to R. Consider the following relations on the set 1, 2, 3, 4. R1, R2, R3, R4, R5 and R6, 6 relations on the set are given. Identify the relations which are reflexive. If you look at the first one, 1 is related to 1, 2 is related to 2, but 3, 3 does not belong to R1. So this is not reflexive. Similarly, R2, it's not reflexive because 2, 2, 3, 3, 4, 4, none of this belongs to R2. What about R3? 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is there. So it is reflexive. R4, 1, 1 does not belong to R4. It is not. R5, 1, 1, then 2, 2, 3, 3, 4, 4. So all these are there, so it is reflexive. So you can see that R1, no, not R1, R3 and R5 are reflexive, whereas the remaining are not reflexive. Now, may I ask the question, is the divides relation on the set of positive integers reflexive? Divides relation, A divides B, is it reflexive? Does A divides A for all positive integers? Of course, A divides A for all positive integers. So it is reflexive on the positive integers. But in place of positive integers, if you take all the integers, is it reflexive? No, because by definition, 0 does not divide 0. Now let us see symmetric and antisymmetric relations. In some relations, an element is related to a second element if and only if the second element is also related to the first element. The relation consisting of pairs x, y, where x and y are students at your school with at least one common class has this property. Because these students are related through that class. One is related to the other one is also related to the first. Other relations have the property that if an element is related to a second element, then this second element is not related to the first. The relation consisting of the pairs x, y, where x and y are students at your school, where x has a higher grade point average than y, has this property. Because x is related to y because the grade of x is higher than y. But grade of y is not higher than x, so y is not related to x. So here is the definition of a symmetric relation. A relation R on a set A is called symmetric if B, A belongs to R whenever the ordered pair A, B belongs to R for all A, B in A. A relation R on a set A is such that for all AB in A, if ordered pair A, belongs to R and ordered pair B, A belongs to R, then A is equal to B is called antisymmetric. Using quantifiers, we can express symmetric relation as for all A, for all B, the ordered pair A comma B belongs to R implies the ordered pair B comma A belongs to R. Similarly, a relation is said to be antisymmetric if for all A, for all B, the ordered pair A comma belongs to R and the ordered pair B comma A belongs to R implies A is equal to B. I can observe that a relation is symmetric if and only if A is related to B implies B is related to A. A relation is antisymmetric if and only if there are no pairs of distinct elements A and B with A related to B and B related to A. That is, the only way to have A related to B and B related to A is for A and B to be the same element. The terms symmetric and antisymmetric are not opposites because a relation can have both of these properties or may lack both of them. So for example, if you take the collection of all ordered pairs where the first element is same as the second element, then it is both symmetric and antisymmetric. A relation cannot be both symmetric and antisymmetric if it contains some pair of the form A comma B where A is different from B. Again, let us ask the divides relation on the set of positive integers. Is it symmetric? Is it antisymmetric? The relation is not symmetric because 1 divides 2 but 2 does not divide 1. It is antisymmetric for if A and B are positive integers with A divides B and B divides A, then definitely A is equal to B. You can just verify this. This is straightforward. Okay, now let us discuss transitive relations. Let R be the relation consisting of all pairs X, Y of students at your school where X has taken more credits than Y. Suppose that X is related to Y and Y is related to Z. This means X has taken more credits than Y and Y has taken more credits than Z. So definitely we can conclude that X has taken more credits than Z. So that X is related to Z under this relation. What we have shown is that R has the transitive property which is defined as follows. A relation R on a set A is called transitive if whenever A comma B belongs to R and B comma C belongs to R, then A comma C also belongs to R for all A, B and C belonging to A. Using quantifiers, this property can be expressed as for all A, for all B, for all C, ordered pair A comma B belongs to R and ordered B comma C belongs to R implies ordered pair A comma C belongs to R. Again, the question is divides relation on the set of positive integers. Is it transitive? If A divides B, B divides C, can you say that A divides C? Yes, of course. If A divides B and B divides C, then there are positive integers K and L such that B can be expressed as A into K and C can be expressed as C equal to B into L and C is A into K into L. So A divides C. So this divides is a transitive relation. We can use counting techniques to determine the number of relations with specific properties. Finding the number of relations with a particular property provides information about how common this property is in the set of all relations on a set with n elements. You already calculated number of relations possible is 2 to the power n square. Out of these 2 to the power n square relations, how many are reflexive? That's what we wanted to determine. For example, how many reflexive relations are there on a set with n elements? For again, you have to use counting principles here. Pairs of the form A comma B where A not equal to B may or may not be in R. Hence, by the product rule for counting, there are 2 to the power n into n minus 1 reflexive relations. There is a number of ways to choose whether each element A comma B with A different from B belongs to R. See, the A comma A ordered pair must be there in the reflexive relation. So there are n such ordered pairs possible. So that definitely has to be there. The remaining ordered pairs A comma B, where A different from B, whether it belongs to the relation or not, it actually counts the number of reflexive relations. So how many are there remaining? N are taken from n square. So remaining are n into n minus 1. So how many such sets possible? That is 2 to the power n into n minus 1. So this explanation is given here. You can please go through that. A relation R on a set A is a subset of A cross A. Consequently, a relation is determined by specifying whether each of the n square ordered pairs in A cross A is in R. However, if R is reflexive, each of the n ordered pairs A comma A for A belongs to A must be in R, right? So each of the other n into n minus 1 ordered pairs of the form A comma B, where A different from B, may or may not be in R. Hence, by the product rule, it follows that 2 to the power n into n minus 1 is the count for reflexive relations. Let R1 be the less than relation on the set of real numbers, and let R2 be the greater than relation on the set of real numbers. That is, R1 is set of all order pairs x comma y such that x is less than y, and R2 is set of all order pairs x comma y such that x is greater than y. Then what are the union of R1 and R2, intersection, the difference, and I say this is the direct sum. We'll define what is the direct sum. Okay, so let us see how to solve this problem. We note that x comma y ordered pair belongs to the union if and only if ordered pair x comma y belongs to R1 or it belongs to R2. Hence, x comma y belongs to the union if and only if x is less than y and x is greater than y. Because the condition x less than y or x greater than y is the same as the condition x is not equal to y. It follows that R1 union R2 is set of all ordered pair x comma y such that x is different from y. In other words, the union of the less than relation and the greater than relation is the not equals relation. Next, note that it is impossible for a pair x comma y to belong to both R1 and R2, because it is impossible that x less than y and x is greater than y. So it follows that intersection R1 intersection R2 has to be the empty set. Now note that R1 minus R2, that is, you remove the elements of R2 from R1. R1 and R2, they are not at all related, right? One is less than relation, other one is greater than relation. So R1 minus R2 is R1. You cannot remove any element from R1 by means of R2. Similarly, R2 minus R1 is R2. And what is R1 direct sum R2? This is R1 union R2 minus R1 intersection R2. And you know R1 intersection R2 is the empty set. So R1 direct sum R2 is the R1 union R2. Now here, how to find the composition of two relations. What is the composite of the relations R and S, where R is the relation from 1 to 3, the set containing 1 to 3, to the set containing 1 to 3, 4, with R given by this collection of ordered pairs. And S is the relation, again, it is from 1 to 3, 4 to 0, 1, 2, with S equal to these ordered pairs. What is the composition of R and S? S composition R is constructed using all ordered pairs in R and ordered pairs in S, where the second element of the ordered pair in R agrees with the first element of the ordered pair in S. For example, the ordered pairs 2, 3 in R and 3, in NS produce the ordered pair 2, 1. See, the second element of the first ordered pair and the first element of this must be same. Then there is a ordered pair 2, 1 in the composition. So compute all such ordered pairs in the composite. We see that X composition R is, say 1, 1 is there and 1, 0 is there. So 1, 0 will be there. Then 1, 4 is there and 4, 1 is there. So 1, 1 will be there. That is here. Next 2, 3 is there, 3, 1 is there. So 2, 1 will be there. 2, 3 is there, 3, 2 is there. So 2, 2 will be there. Then 3, 1 is there, 1, 0 is there, 3, 0. Then 3, 4 is there and here 4, 1 is there. So 3, 1 will be there. So this is how we find the composition. Yes, let us see some exercise problems. I think you can work out these problems. I'll read the question for you. Determine whether the relation R on the set of all integers is reflexive, symmetric, antisymmetric, and or transitive, where order pair X, Y belongs to R if and only if the first relation is not equals, X is not equal to Y. Let's just discuss this. X is not equal to Y. Is it reflexive? Is X is not equal to X? No, this is not reflexive. Is it symmetric? X is not equal to Y. Definitely Y is not equal to X. So it is symmetric. Is it antisymmetric? X is not equal to Y and Y is not equal to X implies X equal to Y? No, never. It is not antisymmetric. Is it transitive? X is not equal to Y. Y is not equal to Z. Can you say that X is not equal to Z? No, you cannot say. X may be equal to Z. So again it is not transitive. Similarly, the other relations, the product is greater than or equal to 1. Then C is X is Y plus 1, 1 more than Y, and X is 1 less than Y. D is X is congruent to Y under modulus 7. E is X is a multiple of Y. If X and Y are both negative or both non-negative. G, X is square of Y. H, X is greater than or equal to Y square. So please try these problems. Then you have a question here. Let R be the relation and S is also given. Find S composition R. You know how to find S composition R. Okay, R1 and R2 with the divides and R2 is a multiple of. So R1 is set of all ordered pairs A, B such that A divides B. R2 is ordered pair such that A is a multiple of B. Find the union, find the intersection, find the differences and also the direct sum. Yeah, please try these problems. Yes, let us see what we have covered in this particular video lecture. We recalled the definition of set, Cartesian product and partition of a set. We also discussed the definition of relation, then some special relations, reflexive, properties of relations, symmetric, antisymmetric and transitive relations. Then equivalence relation, of course, we are going to discuss in the next video lecture. Algebra of relations and composition we have discussed. How to find composition of two relations and what is the union, what is the intersection and how to calculate the differences. Yes, here we end this video lecture. In the next video lecture we discuss equivalence relations and some of their related problems. Thank you. Have a nice day.